So the next chapter, which is what we are going to discuss, is on the AC steady state analysis. Yeah, basically you will be doing the lab and presenting the report tomorrow on power factor, which is related actually to AC steady state analysis, but in a more advanced stage. So in the previous chapter, what we have learned so far in this semester. So at the beginning of the semester, you have learned two new components, two new passive elements, which acts as an energy storage element, energy storing elements. They are the capacitor and the inductor. Okay, and you have learned the behavior, how they store energy and power, and how to calculate the power and energy at particular time, energy storage after some duration of time, some interval of time. Then in the chapter after that, you have learned also about transient analysis. Transient analysis deals when we put constant voltage source. Yeah? We attach constant voltage source to this voltage or current source to this energy storing element, and then trying to determine some of how the parameter, the electrical parameter change within that energy storing element, as a function of time. How the voltage, for example, is being stored slowly into the capacitor, for example. How the current is being stored also in the inductor. The energy is being stored in the inductor. Then you study about switching, circuit that contains switching. So which has, then it means that it has a change, an abrupt change from before the switch is turned on or turned off, and then after that. So the switching action occurs, for example, at t equal to 0 second. So in this case, then you have learned it, you have derived the equation that express the circuit, in terms of first order differential equation. If the circuit contains only a single type of energy storing element, either as capacitor only or inductor only. But when the circuit contains two types of energy storing elements, both inductor and capacitor, then we have second order circuit, in which the equations that explains or describe the circuit has to be in the form of second order differential equation. So you have learned how to solve the equations, and then find the values of particular electrical parameters that are of interest. When now the value has reached certain steady state condition, okay, especially also when the excitation voltage or excitation source is not a constant source, not a DC source, but rather a sinusoidal source, then we deal with the steady state response of the circuit. How the circuit will respond when the signal, when the current or the voltage being put into the circuit is AC circuit. We call it alternating circuit. So the voltage or the current source change with time sinusoidally, either as a sine function or cosine function. And we learn then how then the behavior of the circuit change with the function of frequency. That will be for later. So in this case, we will learn a new kinds of representation of resistance, which we will learn about the concept of impedance here, and and admittance, which basically resemble the concept of resistance and conductance in normal resistive circuit that you have learned in the first semester. After that, then we will learn how to represent AC voltages and currents as complex vector. So first is that you learn how to express them as sinusoidal signal, this AC signal, either AC voltages or AC currents, yeah, a sinusoidal signal, where it contains the amplitude, the frequency, and the phase, then we represent it as a phasor, yeah, as a complex exponential S vector, after which how to represent it in vector diagrams, the AC voltage and currents. Then we will learn how to use the basic circuit analysis laws, like Kirchhoff laws, to solve also the uh, electrical parameters when it is in AC steady state solution. When it is connected to AC source, either AC voltage source or AC current source, and we learn how to use the Kirchhoff law to solve the electrical parameter for the AC. So in this kind of circuit, then it is not changing with time anymore, but because we only it is changing with time because it is AC alternating current. But what we care only is the amplitude and the frequency and the phase change. Yeah, and this is basically what we call as steady state analysis because it doesn't vary with time as what we have learned in the previous chapter where it is exponent minus tx or something like that, yeah, where there is a tau there, etc. And furthermore, after we learn how to use Kirchhoff law to solve the basic AC circuit, then we will learn different analysis techniques, basically similar to what you have learned for resistive networks in semester 1. Yeah, node analysis, loop analysis, Thevenin, Norton analysis. But now, instead of for DC analysis, you will use it for AC signal and AC voltages. Okay, so these are the contents or the subjects which you will be learning in this chapter on AC steady state analysis. So the AC signal, yeah, or AC voltages or currents, yeah, here represented this electrical parameter as xt, yeah. X is a function of t or X is a function omega t. Yeah, usually they are represented as sinusoid function, yeah, sinusoidal function. Yeah, as you know, like this, sinusoidal function has the amplitude xm, yeah, it means it oscillates in the positive and negative region of the signal. Then it has this positive xm and negative xm. Then it has the frequency component omega, which is basically equals to 2 times pi times the frequency. Okay? So the omega here basically equals to 2 pi f. Yeah. Frequency is how many cycles per second. Yeah, if you multiply with 2 pi, then it becomes radian. How many radian per second in the angle or the phase angle per in unit of radian. Then if it is multiplied this omega, yeah, since frequency is dimensionless and radian is also dimensionless. Oh, sorry, so frequency is not dimensional, but it has the dimension of 1 over t, 1 over second. Yeah. So if it is multiplied to t, then this parameter omega t becomes a dimensionless parameter. Okay. And then the xt dimension will be equal to the xm dimension. That is why here the sinusoid can be plotted as a dimensional plot. A dimensional plot means a plot whose x value, whose x-axis does not have any dimension. Omega alone has the dimension of radian per second, which radian basically is dimensionless, while t has the dimension of second. So omega times t is a dimensionless parameter. So this is basically the phase of that signal, pi over 2 pi, and it comes back to the original cycle when it is reaching 2 pi or multiplication, integer multiplication of 2 pi. Okay, so this is xt equals to xm sine omega t. And the characteristic of sine that it is maximum when omega t equals to pi over 2. We can also express this sinusoidal signal as a function of time. Okay, in which case then instead of omega t, we express this as t. So this we divide with omega. Omega, so it's we divide with 2 pi f. Yeah, 2 pi f basically equals to 2 pi divided by t, right? Since because f equals to 1 over t. The frequency equals to the inverse of t. Okay, so if this is divided by 2 pi over t, so this becomes t, right? Pi divided by 2 pi over t becomes t over 2, yeah, half of t. Pi over 2 divided by 2 pi divided by t equals to t over 4. Okay, so these are basically equivalent. Yeah, only the left part is expressed as phase. The x-axis is phase. The function of the sinusoidal signal as a function of phase, which is omega times t, while in the second graph here, the x-axis is t. So the signal is expressed as a function of time. Xm here will be the amplitude or maximum value. Omega is the angular frequency, radian per second. Omega t is the argument in radians. T is the period, yeah, equals to 2 pi divided by omega. Yeah, omega is 2 pi over t, so this becomes t. Period means that if the time is added with the period, the value will come back to its original value. So xt small t here equals to xt plus t for every t, for every value of time. Frequency is the inverse of period, equals to 1 over t, so equals to omega divided by 2 pi. The unit is in hertz or in cycle per second. So omega, the unit is radian per second. Okay. So if we have a constant here added to the omega t, yeah, an angle, a phase angle, yeah, it means that the signal leads the original signal by that phase angle theta. For example, here we have two sinusoidal wave. The first one in gray dash gray line expressed as xm time xm sine omega t plus theta, and the red line is expressed as xm sine omega t. So it means the gray dash line here leads the red wave, yeah, by theta. So there's a difference theta. What does it mean? At 0 omega t, when omega t equals to 0, yeah, the value is already sine 0 plus theta, the value of theta, phase theta. Yeah, so it's not 0 anymore. Well, if it is the original wave xm sin omega t at t equals to 0, the value is 0. Okay, so this is what we call as that the gray dash line wave leads by theta, while the solid red line wave lags by theta. Means it is delayed from the other wave, the gray dash line wave, by theta. Okay, this is the meaning of leads and lags. So if the constant, the parameter after the omega t is a positive, then we know that that sinusoid wave is leading the original one, without the phase addition. If it is negative, omega t minus theta, for example, then it is lagging. Yeah, so let's say let's try to draw the here, for example, when we have another wave that is lagging the red line, the red wave by theta. So here we have here also theta, so like this. So the green wave here is expressed as xm sine omega t minus theta. Okay, so this green wave lags the red line by theta, but this green line lags the dash gray line by 2 times theta. right? By 2 theta. Okay, so far understandable, yeah? No, not difficult, I believe. Then, in order that we, in this particular chapter, since we deal a lot with sinusoids, we express the electrical parameter as sinusoidal signal, it is essential that you review again the basic trigonometry. Please review and remember and memorize the essential identities. For example, sine alpha plus beta equals to sine alpha cosine beta plus cosine alpha sine beta. Cosine alpha plus beta equals to cosine alpha cosine beta minus sine alpha sine beta. Sine minus alpha equals to minus sine alpha, yeah, because in sinusoidal signal it reflects at the point, the origin point, while cosine minus alpha equals to cosine alpha. The cosinus signal reflects at the y-axis. So derived from this, we will obtain also sine alpha minus beta equals to sine alpha cos beta minus cos alpha sin beta. Cos alpha minus beta equals to cosine alpha cosine beta plus sin alpha sin beta. Then sin alpha cos beta, yeah, by adding this and this and this, we will obtain sin alpha cos beta equals to half sin alpha plus beta plus half sin alpha minus beta. Cosine alpha cosine beta equals to half cosine alpha plus beta here plus half cosine alpha minus beta. Okay, then application, some here cosine omega t equals to sine omega t plus pi over 2. So if we put this into this formula, then this equals to cosine omega t sine pi over 2. Sine pi over 2 is sine 90 degrees, yeah, is 1. So this equals to cosine omega t. Then plus cosine omega plus cosine, yeah, cosine omega t sine pi over 2. This one plus sine omega t cosine pi over 2. Cosine pi over 2 is 0. So what remain is only cosine omega t. So let's attempt to write it down. Yeah? So let's see. Using this this identity, okay. So from here equals to sine omega t cosine pi over 2 plus cosine omega t sine pi over 2. Okay. Cosine pi over 2 is 0, right? This is 0. While this equals to 1. So this equals to cosine omega t. Sine omega t equals to, but if we consider also before going to the next line, yeah, cosine omega t, if we draw the graph, yeah, equals to sine omega t plus pi over 2. It means what? This, right? Yeah. So cosine omega t is a sine wave which leads the normal, yeah, leads normal sine by, so this is sine omega t, this wave, right? Well, this wave is sine omega t plus pi over 2. So this wave, yeah, is a wave that leads this wave by pi over 2. Please remember the definition of leads and lags. Okay, so if we look at from here, okay, but we can also find it from this identity, depending on what you are going to understand it, either from these algebraic identities or you can understand from the previous concept, yeah, here in this picture that originates from from the concept of leading and lagging. So on the other hand, then sine omega t is basically a cosine function, but lagging the original cosine function by pi over 2. So sine omega t equals to cosine omega t minus pi over 2. Or if we use the essential identity, this will be equals to, if we use this, we can use this. Okay, so cosine omega t cosine pi over 2 plus sine omega t sine pi over 2. This equals to 1, this equals to 0. So we obtain equals to sine omega t. Then cosine omega t equals to negative cosine omega t plus minus pi. Yeah. So when cosine omega t, this is if it is lagging or leading by pi, and this is the cosine omega t. So again we draw it. This is cosine omega t. If it is leading by pi, so we will have this wave. Yeah. So this is cosine omega t. So for example, this is omega t. Well, this one is cosine omega t plus minus pi. And if you look, this basically is the negative, yeah, the inverse of this wave. That's why cosine omega t equals to negative of cosine omega t plus minus pi. And similarly also with sine. Sine omega t equals to negative sine omega t plus minus pi. Okay, let me erase this. Okay, normally now we will be using radian instead of degrees. Yeah, degrees, maybe you are familiar with degrees in high school and also from elementary school. We often use degrees, yeah, to express angle, yeah, or phase. Well, now we will be using the radian unit more often compared to the degrees. So the connection between the two, the relationship between 2 pi radians equals to 360 degrees. So it means that theta in radians equals to 360 degree divided by 2 pi, or 180 divided by pi degrees. Yeah, this is if you want to convert between radians to degrees and degrees to radian. So in the electrical engineering convention, so you could write either way, either as sine omega t plus pi over 2, or you can write also sine omega t plus 90 degrees. So if you express it as pi over 2, this means that you are using radian. If you use 90 degree, you use the degrees unit. Okay. Any questions so far? Understood or confused or sleeping?
Understandable, sir.
Understand. If you sleep, then you will have quiz. Certain quiz. I like to give quiz, but I don't like to check. Checking it is quite cumbersome, especially when we have answer sheet which is written with very difficult to read handwriting.
Sorry, sir, if my handwriting not good, sir.
Excuse me, Jesse, can you
Sorry if my handwriting not good, sir. The
yeah, as
time,
long
sir.
as it is strong enough, yeah, with strong ink. Yeah, I know.
Oh,
I haven't checked actually your pages. Usually,
oh,
it's
okay, sir.
Alisa. Sorry, Alisa, to mention your name, but Alisa write it with pencil or what? Very thin ink, rather difficult to read. Yeah. So please, if you answer using your own answer sheet, use strong ink, press it really, and take. Do not save your paper space too much. Yeah. So if you use more papers, it's better rather than I have to read very small letters.
Oh, okay, sir.
Yeah,
Okay, sir.
for next quizzes. That's an intermezzo. Anyway, so let's give some example here as a learning example. Here, for example, we have a cosine function. The x-axis, this is dimensionless. Dimensionless. Okay, this is a dimensional plot because now the x-axis is already in the form of phase rather than in the form of time. Yeah? But now we use degrees instead of radian. 90 degrees, 180 degrees, 270 degrees, and 360 degrees. So cosine omega t is drawn like this. Okay, at 0 is 1, the value. At 180 degrees is -1. At 360 degrees, it comes back to the value when it is at 0, which is 1. Okay. So when we have like this now, so the value is 0 when it is at 45 degrees instead of 90 degrees. And at 0 degrees, it has this value. Very difficult to estimate. But the value is 1 when it is at -45 degrees. How to express this in terms of this cosine or sine? Anyone? Cosine? Yes. So it means this wave is lagging or leading.
Which one, sir?
This one, the B wave compared to the A wave here, A signal, this one is leading or lagging?
Leading
Leading by how many degrees?
45
So if it is leading by 45 degrees, it should be written as what? Cosine
minus 45. WT minus 45. Omega T
omega t.
minus 45.
Everyone agrees? Okay, let's check the answer. Who is answering? Martin.
Yes.
Yeah, it's 4 plus. Okay.
Oh, yeah.
Because leading, remember, if it is leading, we write down with positive here. Yeah, the gray dash line is leading the red. That is why the red one is xm sin omega t. The gray dash line is xm sin omega t plus theta. The green one is lagging the red one. That is why we wrote it as xm sine omega t minus theta. Okay. So using that principle, similarly here, this one will be cosine omega t plus 45 degree because this B wave is leading compared to the A wave. Leads by 45 degrees. Yeah. It can also then be written as cosine omega t plus 45 minus 360. You can also write plus 360. Why? Because cosine or sine repeats every 360 degrees. So putting this is okay. However, then we can do further operation on this. 45 minus 360 degrees is minus 315, right? So we can also say, actually, that this wave is a cosine wave that lags the above wave by 315 degrees. Yeah, so it is two ways of saying. So we can say that this is leading or lagging. Lagging is also okay, but then the value of the phase difference will be different. It will not be the same. If we say that this leads compared to the first wave, then it leads by 45 degree. If we want to say it by legs, yeah, by lagging from the previous wave, we just add this phase angle with minus 360 degree. The result is 315 degree. So this wave is basically lagging the first wave by 315 degrees. Okay, so it is two ways of expressing the same signal. Yeah. So the third one, here we have the opposite of the B. function. So this one then means we just need to put negative in front of this expression. Yeah, so this wave is negative cosine omega t plus 45 degrees. However, then we can further simplify negative cosine omega t plus 45 degree. If we look at the previous identities here, cosine omega t equals to negative cosine omega t plus minus pi. Okay, so that value we can just add here negative cosine omega t plus 45 degree. We can convert to cosine omega t plus 45 degree minus 180 minus pi. Pi is 180 degrees, right? Minus or plus, plus minus. Yeah. So this could be either if you choose plus, so this becomes cosine omega t plus 225 degree. If you choose minus, this becomes cosine omega t minus 135 degree. So you can express this as either a cosine wave that leads the first wave, yeah, by 225 degree, or lags the first wave by 135 degrees. Two ways of expression. Or the third way of expression is this one, the negative of a wave that leads the first wave here by 45 degrees. Okay. I hope it's not confusing. It's matter of this one algebraic trigonometry and algebraic trick plus the actual geometrical representation of the wave. Okay, let's give some examples here. V1 equals to V1t equals to 12 sine 1000 t plus 60 degrees. Okay. V2 equals to negative 6 cosine 1000 t plus 30 degrees. Find the frequency and phase angle between these voltages. We have two voltages, V1 and V2. The frequency, yeah, and the phase angle. Now, since they are different, one is sine, the other one is cosine. We have to try to make them as the same function, either as sine or either as cosine. After which then we can determine the phase angle difference between the voltages, the two voltages. The frequency is actually easier. You know, here 1000 t, this is basically equal to omega t, right? Omega t, so 1000 equals to 2 pi. Omega 2 pi f. So dividing this 1000 by 2 pi, we will obtain the frequency. So the frequency in radians per second is the factor of time variable. So this omega is this 1000 per second, 1000 radian per second. So the frequency will be this omega divided by 2 pi, so equals to 159.2 hertz. Now, to find the phase angle, we must express both sinusoids using the same trigonometric function. It's up to you which one you want to choose, either as cosine or as sine, with positive amplitude. And with positive amplitude, yeah, because we don't. So we have to put this negative into the phase terms, yeah, inside the cosine terms. So for example, we use the identity formulas as given in this list. Yeah? So especially the bottom two parts, the bottom two equations, cosine omega t equals to negative cosine omega t plus minus pi, sine omega t equals to sine omega t plus minus pi. Using that identities, then we can express the equation here, yeah, cosine alpha equals to negative cosine alpha plus minus 180 degree. So we can convert this into 6 cosine, yeah, by adding with plus minus 180 degrees. So minus 6 cosine 1000 t plus 30 degrees equals to 6 cosine 1000 t plus 30 degrees plus 180 degrees. In this case, we choose plus. You could also choose negative actually. But if you choose negative, then the phase will be negative. Let's here choose positive, so 30 degrees plus 180 degrees. So this will equal to 210 degrees, right? So 6 cosine 1000 t plus 210 degrees. Now we change the sign here into cosine using the expression that cosine is basically a sine wave that is lagging 90 degrees, leading by 90 degrees. Okay, cosine. It's, yeah, if you are in hesitant, you can always draw again. This is sine wave, while the cosine is this wave. Okay. So expressing the sine, cosine here equals to the sine wave also basically, but already leading by 90 degrees, right? This is cosine. This is cosine, and the other wave is sine. So a cosine wave is a sine wave that leads by 90 degree. So since it is leading, we put plus here, plus 90 degree. Okay, cosine alpha equals to sine alpha plus 90 degree. So 6 cosine 1000 t plus to 110 from here equals to 6 sine 1000 t plus 210 degree plus 90 degree equals to 6 sine 1000 t plus 300 degrees. Okay, so we like to have the phase shifts less than 100 degree in absolute value. So this one is still 300 degrees. We change it to less than 180 degree. How? By using the other, by negative 360. Okay, by negative 360, because of every 360 degrees, both function sine or cosine will repeat again at the same place. Okay, so we can, to obtain phase shift that is less than 180 degrees in absolute value, we just we just add with negative 360 degree. If we add positive 360 degree, this will be even of a value that is positive and larger than 360 degrees, which is not convenient to operate here. So we add this with negative 60 degrees and negative 360 degrees. So the result is 6 sine 1000 t minus 60 degrees. V1t is equal to 12 sine 1000 t plus 60 degree. V2t equals to 6 sine 1000 t minus 60 degrees. So here the phase difference between two is 120 degree. Okay, like this. Then, so it means V1 leads V2 by 120 degrees. Okay, or yeah, V1, this is V1, right? Leads by V2 by 120 degrees, or V2 lags V1 by 120 degrees. Let's have a break for a while, for 5 minutes. Okay, so this one. Wait a moment. Yeah. This one. The answer is shown here. Okay. Example here, we have I1t equals to 2 sine 377 t plus 45 degrees. I2t equal, we have 0.5 cosine 377 t plus 10 degrees. I3t equals to minus 0.25 sine 377t plus 60 degrees. The question is I1 leads I2 by how many degrees? I1 leads I3 by how many degrees? Yeah. So first, for I1 to I3, they are already inside. So what we need to do is just to change the amplitude to positive, and from negative to positive by changing here by with 180 degrees, right? By plus minus pi, or plus minus 180 degrees. From to compare I1 and I2, we need to change this 0.5 cosine into sine function. Okay, cosine alpha again equals to cosine function is basically a sine function that is leading the original sine function by 90 degrees. So cosine alpha equals to sine alpha plus 90 degree. Then, so we can change then I to t, 0.5 cosine 377t plus 10 degrees as 0.5 sine 377t plus 10 plus 90 degrees. Okay. So then this equals to plus 100. This is 10. So this is 100. So the difference between the phase difference between I1 and I2. So this 377 plus 45 minus 377 plus 100, or equals to minus 55 degrees. So I1 leads I2 by minus 55 degrees, or basically I1 lags I2 by 55 degrees. I2 leads I1 by 55 degrees. Yeah, different ways of expressing the same facts. I1 leads I2 by minus 55 degrees. So actually I1 is lagging from I2 by 55 degrees. Okay, then from between I1 and I3, sine alpha equals, we have to convert this negative amplitude into positive amplitude using this identity. Sine alpha equals to minus sine alpha plus minus 180 degrees. So minus 0.25 sine 377 plus 60 degree equals to 0.25 sine 377 t plus 60 degree. In order that we have the phase below 180 degree, we subtract with 180 degree. Okay, we could also use plus 180 degree, but then the phase angle will be larger than 180 degrees. Yeah? So this equals to 0.5 sine. The value of this is negative 120 degrees. So I1 minus I3, here the phase, yeah, 377t plus 45 degrees minus, in parentheses, 377t minus 120 degrees. 377t cancel each other, 45 plus 120 equals to 165 degrees. So I1 leads I3 by 165 degrees. Any questions so far regarding the use of trigonometric identities to express this sinusoidal function or sinusoidal function? No question? Ready?
No, sir.
No, sir.
No, what? No questions.
No question.
It means ready
And no
for,
ready also, sir.
ready.
No ready also.
No ready for what? Yeah.
For quiz.
Quiz.